So again, this is x and this is y, and this is a centroidal acid. This is x prime and y prime. So the moment of inertia Ix prime is equal to the average Ix and Iy plus the difference divided by 2 times the cosine of 2 theta minus Ixy times the sine of 2 theta. Okay? So that's it. So really, you already have everything. So once you know that the angle that you want to rotate the axis is theta, then the moments of inertia about this new axis, it's easily calculated because you already have all the numbers that are needed. Now, the next question is, what is Iy prime? Because you also need that one. Well, you can see it in two ways. You can simply say, well, y prime is just another x prime that was 90 degrees more, right? So all I have to do is just substitute for theta, 90 plus theta. So what would that give you? That would give you the same for this part, right? That same parentheses, and then here you would have cosine of 2 times theta plus 90, right? And then this would be minus, actually I should write it, Ix minus Iy over 2, and this would be Ixy, and this would be sine of 2 theta plus 90. Now, it turns out that if you have an angle like this, which is 2 theta, or actually it doesn't matter, any angle, alpha, if you add 180 degrees, right, the cosine used to have, it's just the same thing, but negative. So if this was something, this is just a negative, right? And the sine, it's also the negative. Now look at this. This right here is cosine of 2 theta plus 180. And this here is sine of 2 theta plus 180. That means that this term and this term just simply change signs, right? Therefore, if we add Ix prime plus Iy prime, that is, we add these two expressions, this thing will add to itself, so we get Ix plus Iy, and this will cancel and this will cancel because the signs change. So you have this relationship, which is kind of interesting. Tells you that the sum of the moments of inertia in the rotated axis at any angle is the same as the moments of inertia before you rotate them. So rotation doesn't change the sum. Therefore, once you calculate Ix prime, it's easier to calculate Iy prime simply by using this relationship, right? Okay? All right. We have one last thing in the toolbox of theory that you need so that you are complete on the theoretical side, and then we just need to get, you know, the knack for applications, for actually being able to do it well, to do it quickly and precisely. And that has to do with the parallel axis theorem for product of inertia. Okay? The parallel axis theorem for product of inertia. It kind of works like this. Let's say that this is the centroid, and this is another set of axes which are parallel to this axis, but are not centroidal anymore. So this is, let's say, x nu, actually I could, well, x nu and y nu. Now let's say that this axis are, the Ixy here is known. What we want to know is what is the Ix nu, y nu, in case we refer them to this axis. let's say that these axes are shifted to the right here a distance ex and shifted upwards a distance ey. So we can say that if we have this point whose coordinates are x and y, we can say that x, you see that distance right there is x nu, right? So you can see that x is just, what is it? No, I don't want x. I want x nu is equal to x minus ex. That's what I want to write. X nu is equal to x, which is this, minus ex. And likewise, y is equal to, y nu is equal to y minus ey, right? Because y is this, and y nu is this piece, right? So, if we write the formula for the product of inertia, x nu, y nu, it would just be xn, yn dA over the area. So substituting these things, we have that y xn, yn is equal integral. Then that would be x minus ex times y minus ey dA over the area. And doing the products in there, you find that I x nu y nu is equal to, this times this is x y dA. Actually, wait, I don't need to write so much. I can just say xy minus xex minus y, what am I doing? xy xey exy, and then plus exey, right? dA. So that's equal. Now the first integral, ix nu y nu. So the first integral is xy dA, that's just y about xy. The next integral is minus ey times the integral of x dA. The next integral is minus ex times, which is a constant, right, times the integral of y dA. And the next integral is ex ey times the integral of dA. So we get that I in the new set of axes parallel is the old one. Then the integral of x dA is 0 because this is a centroidal axis, and by definition that's how we found the centroid. So x dA is 0, y dA is 0, and the integral of dA is the area. Therefore we have plus ex ey times the area. And so we have this, our last formula, which is that the product of inertia, okay, of a set of axes that has been shifted parallel to another set is simply, that is centroidal, is equal to the centroidal one plus the product of the two shifts times the area. Notice that the new value can be smaller or bigger because ex and ey may have different signs. And they are measured from the centroidal to the shift. So in my drawing here, both ex and ey are plus, but if the axis was over here, then ex would be negative and ey would be positive. Okay? So that is the parallel axis theorem or product of inertia. And I believe that we have now at hand all the theoretical tools that we need to do pretty much everything that has to do with bending of cross sections in beams. There are there is one question that often, or not often, that appears in the book. And I'm going to give you the, the tool to solve that question. You don't really need any new theory. It would be something, let's put it this way. I would expect that this is the kind of thing that if you think about it enough, you should be able to just figure it out. There wouldn't, because there's nothing really new that is needed. It's not like, how do you locate the principal axis in this derivation. And the question has to do with, given a cross section, what is the orientation of the neutral axis? Now, the thing to know is that the neutral axis orientation is not a property, because it depends on the loading. So, let's say that we have our axis x and y, and that the principal axes are these. Okay? Now, how do I know what is the neutral axis? The neutral axis is simply a straight line where all the points have zero stress. So now, by definition, the centroid is a point of the neutral axis. And since the neutral axis is a straight line, in order for me to find the orientation of the neutral axis, all I have to do is find one more point whose stress is zero. And that's it. Now, if you want to develop a formula, you can. And let's do it, just for the sake of developing a formula. But really, all you need is to say, given my problem, where is a point where the stress is zero, connected with the centroid, and that is the line. But now let's be formal. So let's say that I have a moment that I'm going to call mx prime, that is going to be plus if it's oriented with the x prime. And let's say that I have a moment my prime that is oriented positive with the y prime. And let's say that I have this point here, and that point is located at a distance, which is what? Y prime from that axis and x prime from this axis. So now, what is the stress at that point? Again, we look at these things always one at a time, as if there was only one thing acting and then the other thing, and you add them together. So if only mx was acting, the stress there would be mx prime times y prime divided by what? Ix prime, right? Now, would that be tension or compression? Well, under the notation that I have here with my thumb pointing out, that would be tension, right? Okay? That would be tension. So let me call it plus. Say tension is positive. Now, if I have only my prime, first let me see the sign. If this moment is like this, that rotates that way, that means the stresses here are going in. So I can see that that would be compression for my prime, and so it would be minus. So then it would be my prime, the distance would be x prime, and the inertia would be y prime. And in order for me to find the orientation of the neutral axis, I want to know where in the world is that thing equal to zero. So if it's equal to zero, this is equal to that, and so therefore mx prime times y prime over ix prime is equal to my prime times x prime over iy prime, right? From where one can state that, for example, y prime divided by x prime is equal to my prime divided by Iy prime multiplied by Ix prime divided by Mx prime. So here is the formula. So given values, of course, this being plus, that being plus, right, you'd have to handle the signs if it was to the left or something, but given the moments that are acting on the principal axis, you plug it in here, that would give you y prime over x prime. Now let's say, for example, that you got y prime over x prime to be 1. Okay? That means simply that this point would be at 45 degrees, right? So this would be the neutral axis. Now 45 degrees with respect to what? With respect to the principal coordinates, right? So remember, the formula relates to the principal coordinates. So actually I want to be clear, so I erase this because it's too messy and just focus on the formula for a second. So if my section was this and my principal axes are that, and let's say I get that y prime over x prime is 1, then that means that I have a neutral axis which is at 45 degrees, right, with regards or with respect to the principal axis. Now, if the problem was such that the question was what is the orientation of the neutral axis with respect to the x, and it turns out that this thing was rotated 20 degrees, then obviously you can see that the neutral axis is rotated 65 degrees, right? Now, you can see that it is not a property of the cross-section because the orientation of the neutral axis depends on properties, but it depends on the applied moments. Okay? Now, that does complete, let me see, I'll double check. Yeah, that does complete everything that has to do with theory and equations for chapter 6 that we're doing. And by the way, all the material that I've been presenting to you now with regards to, what do you call it, product of inertia, rotation, principal axis, and all of that is in the text, and I believe it is in chapter 16. Let me triple check whether that was true or not. Chapter 12, I'm sorry. Chapter 12. So if you go to chapter 12, it's called Review of Centroids and Moments of Inertia. You would be very well advised to take a quick look. And you will find what I've done here, not necessarily in the same way, but well described and so on, and you can always refer to that in case of any doubts. So we now have the tools, and I am going to summarize, not the equations, because the equations you already have. I'm going to try to summarize for you the ideas, okay, as to what is it that we can do and what we are looking at. What kind of situations can we face? What kind of problems are there in the homework and in the exam and so on? What kind of problems? Well, we may have more than one material. So that's one type of problem. The cross-section has more than one material. And without making it crazy, I'm just going to go like this and say the cross-section is like this, and it has material E1, material E2, material E3, material E4. In problems in which there is more than one material, the principal axes are either both known precisely, for example, this case, let's say like this is E1, E1, E2, and these dimensions are the same, A, B, C, right? So in this case, the system is symmetric about this axis, and the system is symmetric about this axis. Those are the principal axes. All right? In this particular case, the system is symmetric about this axis, but the system is not symmetric about this other one. Therefore, the location of this axis must be found. It is not given by symmetry. So, must find y bar, because it's non-symmetric. Symmetric, two axes. Symmetric, one axis. Now, once you have this problem, right, once you find these locations, then this problem is always the same. I mean, the question can be asked in 20 different ways, but it's always the same. You're dealing with the fact that, moment, loads give moments, moments give curvature, curvature gives strain, and strain gives stress. Actually, why am I writing it so small? Symmetric two axis, symmetric one axis. So in this case, loads give moments, moments give curvature, curvature gives strain, strain gives stress. Okay? The key on this kind of problems is that you must be able to locate y bar, and you have to compute flexural stiffness. Which I called in my previous example that you've seen EI effective. I don't know if that's really a great idea or not. It's probably better to just say flexural stiffness, but EI effective is fine. Okay, we have a clear example on how to do that. And then the question could be asked, questions can be asked in many different ways, but it's only this, that's it. So you have more than one material, and you have to answer some question like what is the stress, how big is the moment I can place, and so on. The rest is just thinking. Fundamental, basic thinking, logic, right? The next kind of problem, which is